Okay, this video is about NMR spectroscopy. First of all, NMR stands for nuclear magnetic resonance. And the underlying idea is that atoms that have an odd mass number or an odd atomic number, such as carbon-13 or hydrogen-1, have a property that's called spin. And what that basically means is that if we put these atoms in a magnetic field, their nuclei act like mini magnets that can either line up with or against the magnetic field. The ones that line up with the magnetic field are at a lower energy level. The ones that line up against the magnetic field have got a higher energy level. And we can make the electrons change their field by applying electromagnetic radiation of a particular frequency. The exact frequency that we require to make the nuclei flip their spin depends on a number of things, including the strength of the magnetic field, the type of nuclei, and most importantly, the nuclei's local environment, which means the atoms that surround those nuclei. Okay, so how does this work? It's got to do with shielding and shift. Okay, so if I have a carbon atom, the carbon atom, in the molecule there are electrons, and the electrons provide some shielding from the magnetic field. If we've got another atom close to the carbon, so in this case here I've got chlorine close to the carbon, the chlorine is highly electronegative, so it is going to pull the electrons away from the carbon, and that's going to remove some of the shielding. So the carbon is going to be de-shielded. And what we can see in the diagram here on the right is that the effect is going to be strongest for the carbon that is closest to chlorine, and it's going to be weakest for the carbon that is the furthest away from chlorine. Okay, so being attached to atoms that are highly electronegative can cause de-shielding. Now, some terminology, we're going to be talking about upfield, downfield, shielded and de-shielded, and high frequency and low frequency. Those atoms that are still heavily shielded, so their electrons haven't been pulled away, they're going to require lower frequency electromagnetic radiation to cause the spin to flip. Okay, so we're going to see them in this region here of the NMR spectrum. So they're going to be upfield to the right. The ones that have become de-shielded, so the electrons have been pulled away from those atoms, they're going to be further downfield, so further to the left, and it's going to take higher frequency electromagnetic radiation to cause these nuclei to flip their spin. Now, so we said that chlorine atoms or other highly electronegative atoms can cause about a shift. The other thing that can cause a shift are particular functional groups. This picture here shows us where we would expect the carbons that are associated with particular functional groups to show up on the NMR spectrum. Now, on your data sheet, you've got something similar to this. So you've got some values given to you on your data sheet that can give you clues about the functional groups that are in the molecule based on the NMR spectrum. Most importantly, though, a carbon NMR can give us some information about the number of carbon atoms in a molecule and also how these carbon atoms are connected up. So if we've got carbon atoms that are not equivalent, which means that they've got different atoms surrounding them, they're in a different local environment, then those will appear as distinct peaks on the carbon NMR. So we can see in this first molecule over here, we've got two carbon atoms. They are not equivalent because if we have a look at what is attached to those carbons, they've got different things attached, so they're not equivalent to each other. And they appear as different peaks on the electromagnetic spectrum. Now, one thing that's interesting is that we can see that this carbon over here is going to be the one that's further downfield because the oxygen is pulling away some of the electrons from the carbon, and so it is de-shielding the carbon. Okay, but the most important thing is we can see we've got two carbon atoms that are not equivalent, so we've got two peaks. Okay, and this over here, that's a solvent peak, so we ignore that one. Now, this other molecule over here, this molecule's got 5 carbons, but some of the carbon atoms are equivalent. So if we look at these 2 carbons circled in blue, for example, these 2 carbon atoms are attached to the same thing. So they're attached to 3 hydrogens, and then this whole string of carbon atoms over here on the other side. So they're basically a mirror image of each other. They're attached to exactly the same thing, so they are equivalent carbons. The two that are circled in orange, again, they're equivalent carbons. On one side, they've got a methyl group, and on the other side, they've got 3 carbons attached to hydrogens. So both of these carbons are attached to exactly the same thing. So again, a mirror image of each other. So they are equivalent carbons. This other carbon over here is not equivalent to any. So what we can see in this carbon NMR is that there are 3 peaks. The other thing that's interesting about this carbon NMR is that one of the peaks is significantly shorter than the other 2. Now, what actually matters, it's not the height of the peak that matters, it's the area under the curve. So the area under the curve for these 2 peaks would be equal, and this one would be about half that size. And the reason that happens is that these peaks correspond to 2 carbons, whereas this one here corresponds to 1 carbon only. Now, in your OneNote, you've got a page called Carbon NMR Practice. If I could encourage you to go back to that page and have some practice at working out how many peaks you would expect on the carbon NMR based on the structure of the molecule. Now, the other thing you need to know about is proton NMR. Proton NMR is the same sort of idea, but this time it's the hydrogens rather than the carbons that are responsible for the signals in the spectrum. And obviously there are a lot more hydrogens. The other thing that's interesting about the proton NMR is that we get some splitting of peaks. So if we have a look at this molecule over here, we've got 1 hydrogen atom over here. And then we've got these 2 hydrogen atoms that are equivalent to each other. So that's the reason why we have 2 signals. But you'll notice that these signals, these peaks, are split. And the rule that applies in terms of splitting is that what causes the peaks to split are the hydrogen atoms on the neighboring carbon. So this hydrogen over here, on the neighboring carbon, there are 2 hydrogens. So it's going to split into 2 plus 1. It's going to split into 3 peaks. Okay, so you can see that the red peak is split into 3. On the other hand, the 2 hydrogens that are colored in purple, on the neighboring carbon, there's only 1 hydrogen. So that peak is going to split into 1 plus 1, which is 2. So you can see there are 2 peaks. This one is split into 2. So the rule is that the peak is split by the hydrogens on the neighboring carbon, and it's split into n plus 1, where n is the number of hydrogen atoms on the neighboring carbons. Now, again, in your OneNote, you've got a page that's called Proton NMR Practice. So if I could encourage you to have some further practice at doing this, but I've just got a couple of examples here on the screen. So if we have a look at this molecule over here, we can see that all of these hydrogens here are equivalent. So that would produce 1 peak. And that peak will be split by these hydrogens. So it'll be split into 3. Okay. Now, the hydrogens that I've circled in green, that corresponds to another peak. And that peak will be split into 7 because it will be split by all of these hydrogens and all of these hydrogens. So that's 6 hydrogens all up. So it'll be split into 7. Okay. Now, in the second molecule over here, we're going to have 3 peaks. Peak A, that corresponds to these hydrogens. Peak B and peak C. Peak C is not going to be split at all because there are no hydrogens attached to the neighboring carbon. Peak B is going to be split into 4 because the neighboring carbon has 3 hydrogens attached. And peak A is going to be split into 3 because the neighboring carbon has 2 hydrogens attached. So if I could encourage you to get some further practice at this. Okay, hopefully this helped you out.